Sometimes, in low light, the sharp outlines of letters dissolve into soft blurriness. Not because the world has changed, but because your retinal cells are quietly adapting. What if that blur is not simply age, but biology asking for attention? Hi, I'm Dr. Melina, a longevity researcher, and I want to begin with a quiet truth. Vision loss is rarely sudden. It is usually the result of years of silent cellular stress unfolding beyond awareness. Many adults over 60 notice dry eyes, difficulty driving at night, or the need to hold a phone farther away. The American Optometric Association notes that our eyes become more vulnerable with time, yet vulnerability is not the same as inevitability. Inside the retina, millions of photoreceptors depend on mitochondria, tiny power plants, to convert light into meaning. As oxidative stress accumulates and inflammation lingers, these cells enter a state resembling cellular senescence, less resilient, less efficient. Here is the paradox few discuss. Much of this microscopic wear intensifies at night. During sleep, circulation patterns shift, oxygen delivery fluctuates, and repair systems must work with whatever nutrients remain available. If the eye lacks protective antioxidants, the darkness becomes an opportunity for damage rather than renewal. So the real question is not whether aging happens, it does, but whether nighttime biology can be supported differently. And what if something as simple as a fruit, timed precisely, could change that overnight equation? If nighttime is when the eyes are most vulnerable, it is also when they are most capable of repair. Inside the retina, mitochondria labor through the dark, generating energy while neutralizing reactive oxygen species, unstable molecules that accumulate through oxidative stress. When this balance falters, inflammation quietly rises, and proteins within the lens begin to stiffen through glycation, a slow caramelizing of tissue that clouds clarity over time. Have you ever wondered why vision often feels worse upon waking before the light fully returns? During sleep, oxygen tension in retinal tissue can subtly fluctuate, a phenomenon sometimes described as transient retinal hypoxia. Photoreceptors, among the most metabolically active cells in the body, depend on constant fuel. Without sufficient antioxidant support, compounds like lutein, zeaxanthin, anthocyanins, cellular membranes become more susceptible to lipid peroxidation. DNA inside these light-sensitive cells faces cumulative wear. Even the blood-retinal barrier, that selective shield protecting neural tissue, can become more permeable under chronic inflammation. Yet darkness is not the enemy. It is the stage for autophagy, the cellular recycling process that removes damaged components and renews function. When nutrients that assist these pathways are available, repair mechanisms become more efficient. When they are absent, degeneration quietly accelerates. This is why aging vision behaves less like fate and more like neglected maintenance. The eye is not passive. It responds to biochemical signals. The question becomes, what signals are we sending before sleep, and what raw materials are we providing for that nocturnal repair? Because the difference between decline and resilience may begin long before morning light. When vision begins to blur, the modern response is often immediate relief. Lubricating drops for dryness, brighter lenses for reading, surgery when cataracts advance. These interventions can be valuable, even transformative. Yet relief is not the same as renewal. Have you ever noticed how rarely we ask why the tissue changed in the first place? Much of age-related visual decline traces back to oxidative stress, chronic low-grade inflammation, mitochondrial inefficiency, and glycation, processes studied in the same framework as other chronic diseases. Researchers now describe aging itself as modifiable biology, influenced by environment, metabolism, and cellular signaling. The retina, as neural tissue, reflects these systemic forces with remarkable sensitivity. Emerging evidence suggests that dietary antioxidants and polyphenols can support photoreceptor resilience and macular integrity, with some trials reporting slowed progression of degenerative changes when specific carotenoids are abundant. Age-Related Eye Disease Research Group, 2001. Compounds such as zeaxanthin and anthocyanins appear capable of reinforcing the macular pigment and reducing inflammatory signaling. This is not magic, and it is not a substitute for professional care. It is education, an invitation to understand that biology responds to inputs. So, instead of asking only how to correct blur, a deeper question forms. How do we reduce the biochemical forces that create it? If nighttime is when stress accumulates and repair activates, then the hours before sleep become strategically powerful. And this is where a simple, almost overlooked ritual begins. Not with a pill, but with a countdown. 7 fruits. 1 descending promise. 7 fruits. Not exotic miracles, not pharmaceutical inventions, but biological messengers timed to meet the eye's nocturnal repair cycle. Imagine descending a staircase from 7 to 1, each step offering a different layer of protection. What if the final hour before bed became less about habit and more about signaling your cells to prepare for restoration? At 7, we begin with kiwi. Small, unassuming, yet rich in lutein and zeaxanthin, carotenoids that function as internal blue light filters. These pigments accumulate in the macula, forming a protective shield against oxidative stress. Kiwi also contains natural serotonin precursors that may support circadian alignment, indirectly enhancing the quality of restorative sleep. When sleep deepens, autophagy and mitochondrial repair intensify. Could a simple green fruit help synchronize that rhythm? At 6 stands watermelon, abundant in lycopene, a carotenoid studied for its antioxidant capacity. Lycopene circulates through lipid membranes, potentially stabilizing retinal cells against free radical damage. Its high water content also supports vascular flow, and circulation is the quiet courier of oxygen to photoreceptors. At 5 come black currants, dense with anthocyanins, pigments that give them their deep purple hue. Research suggests anthocyanins may support dark adaptation and reduce inflammatory signaling within ocular tissues. In dim environments, the retina must recalibrate rapidly. Wouldn't it make sense to nourish that recalibration before sleep? We are only halfway down the staircase, and already the chemistry of night begins to shift. But the next layers go deeper, crossing barriers, delivering oxygen, protecting DNA itself. And what waits at 4 may surprise you. 4 brings us to wild blueberries, darker, smaller, carrying concentrated anthocyanins and a compound called pterostilbene. Unlike many antioxidants, pterostilbene is structurally suited to cross lipid barriers with relative ease, potentially reaching delicate neural tissues protected by the blood-retinal barrier. Inside photoreceptors, DNA absorbs constant light exposure. Oxidative byproducts accumulate like microscopic sparks. Polyphenols, such as these, are being studied for their capacity to modulate inflammatory signaling and support mitochondrial resilience. Have you ever considered that protecting vision may be less about brightness and more about defending microscopic strands of genetic code? 4 brings us to red dragon fruit, vivid as a sunset. Its betalains are associated with nitric oxide pathways, which influence vascular dilation. Oxygen delivery to retinal tissue is critical. Even subtle reductions can amplify oxidative stress. Supporting circulation before the long metabolic stillness of sleep may help balance that overnight equation. The retina does not rest simply because we close our eyes. Descending further, we approach 2 goji berries, small but densely pigmented with zeaxanthin. Zeaxanthin accumulates selectively in the macula, forming what researchers call macular pigment optical density, a measurable shield correlated with visual performance in aging populations. Some observational studies suggest higher intake aligns with slower macular degeneration progression, though outcomes vary. And then there is 1, papaya. Within its golden flesh lies papain, an enzyme studied for its role in protein breakdown. Glycation stiffens lens proteins over time, contributing to opacity. Could enzymatic support influence that process? We have reached the bottom of the staircase, but understanding how to unlock these compounds changes everything. Reaching 1 is not the end of the descent, it is the moment of precision. Papaya stands at the base of our countdown because glycation is one of the quiet architects of clouded vision. When excess glucose binds to proteins in the lens, advanced glycation end products accumulate, stiffening what was once flexible and transparent. Over years, clarity diffuses. Papaya contains papain, a proteolytic enzyme studied for its capacity to assist protein turnover in various tissues. While no fruit reverses cataracts, supporting systemic metabolic balance may reduce the biochemical environment that accelerates glycation. Have you ever wondered whether the fog of aging begins long before you notice it? What makes these 7 fruits compelling is not fantasy, but convergence. Carotenoids like lutein and zeaxanthin concentrate in retinal tissue. Anthocyanins influence inflammatory pathways. Polyphenols interact with mitochondrial signaling. Betalains touch nitric oxide biology. Each compound whispers to a different cellular mechanism. Yet chemistry alone is not enough. Bioavailability, the body's ability to absorb and deploy nutrients, determines whether these molecules reach the retina at all. A fruit eaten carelessly may pass through unnoticed. The same fruit, timed and paired strategically, may become a signal. So the question becomes less about which fruit is best and more about how to prepare the body to receive what it offers. Because even the most powerful antioxidant cannot protect a cell it never reaches. And that is where 5 simple rules quietly transform intention into impact. 5 rules, descending again, not of restriction, but of optimization. At 5, timing. Research in circadian biology shows that nutrient metabolism shifts as evening approaches. Consuming antioxidant-rich foods roughly an hour before sleep may align circulating compounds with the window when autophagy and cellular repair intensify. The body keeps a schedule, even when we ignore it. At 4, healthy fat. Carotenoids, such as lutein and zeaxanthin, are fat-soluble. Without dietary lipids, absorption may diminish significantly. Pairing fruit with walnuts or a small portion of avocado can enhance micelle formation in the gut, increasing uptake into circulation. It is not excess, it is synergy. At 3, temperature. Enzymatic activity, including that of papain, is influenced by heat and cold. Extremely chilled fruit may reduce enzymatic efficiency. Allowing fruit to reach room temperature before consumption respects its biological design. At 2, gentle washing. Vigorous scrubbing can remove delicate surface polyphenols, especially on berries. A careful rinse preserves more than appearance. At 1, separation from heavy dairy. High calcium environments may compete with the absorption of certain plant compounds, though findings vary. Spacing dairy intake away from antioxidant-rich fruit may support cleaner uptake. These are small calibrations, almost invisible habits, yet biology often responds to small, repeated signals. Have you ever noticed how minor rituals, repeated nightly, become identity? Because beyond chemistry lies something deeper, the night shift within your cells, already waiting. When darkness settles and the body grows still, metabolism does not sleep. Insulin sensitivity subtly shifts, growth hormone pulses, and autophagy, the cell's internal recycling system, increases its quiet work. Damaged mitochondria are dismantled, misfolded proteins tagged for removal. This nocturnal maintenance crew depends on metabolic flexibility, the ability to transition between glucose and fat-derived fuel. Could a strategically timed, moderate fruit intake support this balance without overwhelming it? Polyphenols found in berries and carotenoids in brightly colored fruits have been studied for their influence on signaling pathways linked to NAD+ metabolism and sirtuins, enzymes sometimes described as guardians of cellular time. While outcomes vary across populations, laboratory research suggests these compounds interact with oxidative stress pathways and inflammatory mediators. The retina, with its immense energy demand, reflects these systemic dynamics rapidly. What matters most is not dramatic intervention, but alignment. When circadian biology, nutrient availability, and sleep quality converge, repair becomes more efficient. When they conflict, late heavy meals, erratic sleep, chronic inflammation, stress accumulates. Imagine an older adult who once avoided night driving, now noticing slightly sharper contrast at dusk. Not perfection, just resilience. Biology rarely shouts, it adjusts quietly. Have you considered that your eyes may be less fragile than you were told, and more responsive than you assumed? Because nourishment without movement is incomplete, and the retina listens closely to how the entire body moves. Vision does not exist in isolation. It mirrors cardiovascular and metabolic health. Exercise influences gene expression in ways that ripple toward the retina. Aerobic activity enhances vascular elasticity and supports nitric oxide production, improving blood flow to delicate neural tissues. Strength training preserves mitochondrial density, sustaining the energy demands of photoreceptors. Studies consistently associate higher cardiorespiratory fitness, often measured as VO2 max, with reduced risk of age-related chronic disease. Could the same systemic resilience extend to the eyes? Movement also improves insulin sensitivity, indirectly moderating glycation stress. When glucose regulation stabilizes, fewer advanced glycation end products accumulate in proteins throughout the body, including the lens. The connection is subtle but profound. What strengthens the heart may protect the retina. Yet biology is not only mechanical, it is psychological. Habits form identity. A nightly bowl of antioxidant-rich fruit, a consistent sleep window, regular movement. These behaviors become signals not just to cells, but to self. An older woman reading to her grandchild without squinting does not see polyphenols at work. She experiences continuity. Have you ever asked yourself whether protecting vision is truly about eyesight or about preserving independence? Because beyond nutrients and mitochondria lies a deeper force shaping longevity, connection, purpose, and the belief that change remains possible. And this final layer is maybe the most powerful of all. Independence is rarely lost all at once. It recedes in small hesitations, avoiding evening walks, declining invitations after sunset, surrendering the car keys reluctantly. Vision is more than optics, it is autonomy. Psychological research in aging populations consistently shows that a sense of purpose and social connection correlates with longer health span. Chronic loneliness, by contrast, elevates inflammatory markers and stress hormones that influence cellular aging. The retina, like the brain, responds to systemic inflammation. Consider how rituals anchor identity. Preparing fruit before bed, choosing colors rich in carotenoids and anthocyanins becomes more than nutrition. It is a declaration. My biology is worth supporting. When individuals adopt small, consistent behaviors, neural pathways reinforce commitment. Discipline in this context is not rigidity, it is self-respect. Sleep deepens when anxiety softens. Cortisol declines, melatonin rises, and circadian rhythms stabilize. Under these conditions, cellular repair, including mitochondrial renewal and protein turnover, proceeds more efficiently. The retina benefits from the harmony of the whole organism. Have you noticed how hope itself can feel physiological, as if posture straightens and breath steadies? The science of longevity increasingly converges on integration, metabolism, movement, light exposure, emotional resilience. No single fruit guarantees clarity, but combined signals, biochemical and psychological, reshape trajectory. And when we step back from the microscope, a final question emerges. What future are you preparing your eyes to witness? Because the story of aging vision is not finished. It is responding. Aging has long been described as decline, as though time moves in only one direction. Yet modern biology tells a more nuanced story. Cells respond to environment. Mitochondria adapt to demand. Inflammatory pathways quiet when triggers lessen. Even telomeres, protective caps on chromosomes, appear influenced by lifestyle patterns over years. The body listens. The eyes, delicate extensions of the brain, are not exempt from this responsiveness. When oxidative stress overwhelms, damage accumulates. When antioxidant capacity strengthens, equilibrium improves. When glycation rises unchecked, clarity dims. When metabolic health stabilizes, tissues endure. These are gradients, not guarantees. Imagine yourself months from now, reading in evening light without strain, noticing sharper contrast at dusk. Perhaps the change is modest. Biology often rewards consistency quietly. The ritual of descending from 7 to 1, kiwi to papaya, becomes symbolic, a reminder that care is cumulative. This conversation is educational, never a substitute for professional medical guidance. But education empowers awareness. Awareness shapes behavior, and behavior repeated nightly becomes biology. Have you ever considered that the difference between fading and flourishing may lie in what you choose consistently, not dramatically? The future is not something that happens to your eyes. It is something your cells negotiate each night. And tonight, you hold more influence than you think.